So I'm happy to introduce Leilani Gilpin. She's a PhD candidate in EECS at MIT. She works on enabling autonomous vehicles and other autonomous machines to explain themselves. Before MIT, she worked as an engineer at Parse, focusing on anomaly detection in healthcare. She has an MS in computational math and engineering from Stanford, and a BS in math and computer science from UC San Diego, and is a recipient of NSF Graduate Fellowship, Stanford School of Engineering, and is MIT UCEM Sloan Scholar. And we're very happy to host her to visit ISI today. So over to you.
Great. Thanks, Terry, for that nice introduction. If the volume or anything goes out, just sort of let me know. Zoom is always a little bit buggy, but I'm excited to be here today. I'm going to be talking about some of my thesis work, in particular, something I call anomaly detection through explanations, which is sort of a new way to think about doing error, failure, and anomaly detection using symbolic explanations. And so the outline for today, I'll start by motivating the problem. So I'll be talking about the problem that complex systems fail in very complex ways. I'll focus on autonomous vehicles since that's largely been the application that I've been working on in my thesis work, but this is also applicable to other types of complex systems, including ones with people. I'll talk about one type of solution. So I'll talk about reasonableness monitors, which are local sanity checks that you can use to wrap around one of these subsystems that can detect and justify whether they're behaving reasonably or unreasonably. And finally, I'll tie that into full system design. So I'll talk about how I created a system architecture towards a self-explaining architecture that can basically explain when things are wrong. And it can also sort of reason about these internal disagreements. And that's all leading to more robust failure reporting. So starting with the problem, I had sort of alluded to that these complex systems fail in complex ways. And I think one of the best examples of that are these opaque machine learning systems, largely deep neural nets and convolutional neural nets. And one of the best examples we have of these failures are adversarial examples. So this is something where you might have an image recognition system that's trying to label different images. So perhaps this picture, it says that it's a pig, but with a little bit of noise, so something that we can't see as humans, all of a sudden that fools the network into thinking that this is an airliner. And the biggest problem with something like this is largely they fail without cues. So they have no idea when they fail in these cases. They can't tell when they're different than another. And these only become amplified when they start being put on, safety critical systems like self-driving cars. And a lot of these systems, a lot of these image recognition systems are actually running on the self-driving cars today. In fact, there was an example of this. There was an AI that mistook a bus side ad for a famous CEO in China and actually charged her with jaywalking. And the picture on the bus was something like this. Now, this is a case where if you showed this even to a small child, they would tell you that that is clearly not someone jaywalking or crossing the street. And these failures, although, when seen in isolation and just a deep neural net doing image recognition, when they're put on top of these safety critical systems, we have these failures with immense consequences. But this is not just, for fully autonomous systems. This also includes complex systems with people. In fact, one of the biggest problems in autonomous systems is the communication between a human operator and an autonomous operator, especially in these sorts of failure cases. And this is largely due to a lack of communication and a misalignment of expectations. In fact, in a sort of small complex system, if you look at the roommates in my apartment here, we have an expectation that we will all be sharing food. In fact, we have that as sort of a rule in our house. Everyone goes out and gets their own groceries, and then we share the food amongst us. But if there's an expectation that there will be something there in the morning, like someone's yogurt, but someone didn't communicate to the rest of the group that they ate the whole thing, then we can have this sort of misalignment, and this can cause a lot of animosity, especially between parts. Now, well-built human organizations have the structures to deal with these types of flaws and failures. Maybe we didn't have that as much in my living community. And so my thesis question has largely been, how do we do this for machines? So how do we take the structure of human organizations and then use that to explain and reconcile these types of failures and errors in complex systems? And that's largely been the focus of my thesis work. So I've been inspired by human organizations, and largely I've added two different parts. So I've facilitated a better communication amongst parts, and that's using symbolic explanations. And then I've also added these reasonableness monitors or sanity checks around all of the subsystems to make sure that they're also behaving reasonably in their own local sort of neighborhood. And so if we think about the sort of requirements for this, and we look at a human organization like something here, then you largely have sort of three parts. So you have the organizational aspect, and I've arranged this as a hierarchy of overlapping committees. And it's important that they're overlapping because if there are issues, so if they're sort of disagreeing on something, you want to make sure that more than one are actually overlapping in these beliefs. So you can think about this as sort of the red system here to the left as being software engineers, and maybe the blue part are quality assurance engineers, and then obviously there are people in between that do both development and testing. And then you also have continuous interaction and communication. In fact, we've seen in software engineering that this type of agile programming and scrum meetings actually work really well to be able to diagnose these types of errors and failures. And so that's largely what I did with this local subsystem monitor. The idea is that the parts are always explaining to themselves what they're doing and why it's reasonable or not. And then I used that and applied that to full system design. And so the idea is that when a failure occurs, then we can make a story by looking at the underlying explanations of the underlying members. And that's what I did with something that I call an explanation synthesizer. And that's able to basically compile the explanations from the underlying parts, which are from the local reasonableness monitors. So it figures out which ones are right and wrong in these circumstances. And this architecture actually does a very good job. It actually is able to mitigate a lot of the common problems that we've seen in self-driving cars. So the local subsystem monitors are really good at looking at new scenarios and situations we haven't seen before. It's been shown that self-driving cars are trollable, or they can be fooled in lots of different ways. And the nice part about a reasonableness monitor is that the rules and the reasons that they use are very abstract. So they can sort of justify and reason about new situations. It can say that something like a moose crossing the street is a large object that should be avoided, even if it doesn't know what a moose is. And then something like the explanation synthesizer is really good at dealing with issues where you have inconsistencies between subsystems or parts. And that's exactly what caused the Uber self-driving car accident. I'll go into that in more detail in the later part of the talk. But again, that can deal with these sorts of conflicting reasons. And so if you have a system like the LiDAR that's perceiving these low-level details but doesn't really understand, and the vision system, which can be easily fooled, but it's able to usually detect these objects with a very high accuracy, it can deal with those when they disagree, which is fairly often. So again, I'll be looking at the Uber accident mostly for the remainder of this talk. And I'll just give you a sort of preview of what happened. So you'll see here, there's a woman crossing the street with a bicycle. She sort of comes out of the shadows. And what happened is that the LiDAR had detected the person with enough time to stop, but the vision system was oscillating between a bunch of different labels. In fact, it had never seen a person walking a bicycle like that before, so it didn't know how to label it. And the high-level planner decided that that was something that should be ignored. Again, I'll sort of revisit that later in the talk. But my monitoring system architecture is actually able to reason about this circumstance. So using monitoring and communication, I am able to reconcile this type of situation. And so the output of my system, which I'll go through in a little bit more detail later, says that the best option in this case, and this is done after the fact, is to veer and slow down. The vehicle is driving too fast to suddenly stop. The vision system is inconsistent, but the LiDAR system has provided a reasonable and strong claim. It's able to understand that there is an object moving across the street. And you can sort of see where the different parts of the explanation come in here. You can see that the tactics, the actual vehicle state is important to figure out what the next action should be, as well as figuring out that the vision is inconsistent. And then the LiDAR also has some understanding. And I'll be using this as a motivating example throughout my talk. But first, I'm going to talk about these local subsystem monitors. So in particular, I'm going to spend a little bit of time talking about error detection for local subsystems. And in particular, I'll be talking about opaque subsystems like deep neural networks. So to be able to do this sort of reasonableness monitoring, I consider the fact that a complex system can largely fail in two ways. And again, when I'm talking about a complex system, that is a system that's built out of multiple parts. So you can consider that the failure is local, so it's due to a module failure that can be basically traced back to a specific subsystem, or it can be a failed cooperation amongst these subsystems. And I'm going to be focusing on this local type of failure first, and then I'll move towards this failed cooperation in the later part of the talk. In particular, I built reasonableness monitors for multiple parts of the car. In particular, I built that for the camera and the LiDAR unit, but I'm going to focus mainly on how I do that for the camera system. So the way that the camera system and vision works on a self-driving car is that you usually have a neural network or a convolutional neural net label that camera data. So what this looks like is you largely get an image. So you would get something like this person crossing the street, and you would want to sort of figure out what this thing in the blue box is. So that is largely passed through some sort of deep neural network. For a while, the Inception network at Google was doing particularly well. And what you get out of this system is a label, and in this case, you get something like a pedestrian. Now, as I alluded to in the introduction here, these neural networks are extremely brittle. Again, they're prone to be fooled by these sorts of adversarial examples where if you add a little bit of noise, it classifies the image as something different. But this is also, these types of adversarial attacks have also been done in the real world. In fact, it was shown with just a couple pieces of tape. A deep neural network would perceive the stop sign as a 45-mile-an-hour sign, and then it would actually proceed through the stop sign. And so you can imagine the types of consequences that this could have. And these types of hacks are endless. They've shown this with graffiti and all sorts of different things that are regularly found in the physical world. And so while people may sort of explain away these types of adversarial examples as not being important, I argue that when we look at critical applications, even in security, but in my focus of self-driving, these mistakes have large consequences. And so what my solution has been is to monitor their outputs for reasonability. So the way that I do this is I look at the input and I treat this sort of internal processing, this deep neural network, as an opaque mechanism. So I just say that I'm not going to understand what's going on there. And this is important for two reasons. One is that sometimes these algorithms are opaque because they're too difficult to understand and too complex. But if you look at self-driving, a lot of these algorithms are proprietary. So even if they were interpretable and we could understand what they're doing, a lot of these algorithms are actually trade secret. And so it's important to sort of treat them as a black box. And so then what I did is I looked specifically at the output and supplemented that with common sense. So I took some common sense knowledge. I represented that in a flexible way. And then I created a rule to be able to, or a set of rules to be able to identify unreasonability. And that's all leading to a justification of whether that is unreasonable or not, given the context that you're in. And so again, this is all leading towards a justification of whether the output of one of these systems is reasonable or not, and a justification of why. And so the way that this architecture looks is it's largely built out of those parts. So I take the output of some sort of opaque mechanism that could be anything from instructions from a vehicle planner or the outputs of an image recognition system. I represent that in a common form, and then I use a set of rules to identify whether it's unreasonable or not, and that leads to a justification or explanation. Now I'm going to walk through some of the parts of this in some detail. I'm going to start by how I actually identify unreasonability. So this is largely done with a constraint checker with a set of rules, which is again leading to a justification of whether it's reasonable or not. Now, one of the things that you do have to do, I'm sort of from a classic AI context, is you do have to start with some baseline rules. And so one thing that I did was I largely parsed the driver's handbook. I look at the driver's handbook of Massachusetts. And basically I represented that in a common rule language. And so I automatically parsed that. So I had, I basically wrote a reader to be able to look at that and search for if-then rules. And then I manually went through and weeded some of those out. And I'm happy to sort of talk about that offline. But what this actually looks like is, so I take these rules and then I represented them in a common rule language. I chose to use AIR, which stands for A more than RDF. And I'll sort of get back to the reason why I chose to use this language, but it was largely because a lot of the information that I used was in RDF because I was using a Commonsense knowledge base that stored its information in RDF. But what's nice about this is that these rules also have reasons attached to them, which nicely led to an explanation at the end. Now, you can't just represent all the circumstances that you want in this sort of rule language. So you also have to have a reasoner that can sort of figure out when these rules have not been triggered or when they have. But I also wanted to create the ability to be able to learn some of these rules from experience. And I think this is sort of nicely illustrated with an example. This is a parking structure that I encountered at my undergraduate at UC San Diego. And this is an example of what happens when an existing rule doesn't actually apply in that context. So I was driving down this parking structure. You can see it's fairly tall, and I perceived someone that was flashing their high beams at me. And my previous rule said that if someone was flashing their high beams at me, that meant that I should turn on my lights. But this doesn't make any sense in this sort of context. It was a nice shiny day. It was in San Diego. And so that baseline rule just doesn't apply in this context. And this happens a lot in self-driving where you see new things and these previous rules don't apply. And so what this actually was is a warning signal. If I was in a parking structure or something with narrow passageways, flashing high beams could mean a multitude of different things. But in this case, it was largely a warning signal. And that's the new rule that I want to create. And so the idea that I had is, what if you could sort of introspect on these justifications and explanations that you got? If you looked at the description of state and what you were perceiving, could you actually learn these sorts of behaviors? And largely what we showed is that you largely could. And so what I did was basically create this ability to learn rules by examining the explanations from my reasonableness monitor. So the idea is that if you look at this, the output explanation, so in this case, if you look at the fact that you're in a parking structure, they're very narrow passageways, it's well lit, can you then learn a rule from that explanation? And so if there's a new rule, you can sort of update your rule base in the system. Otherwise, you say that there's no rule made. And so again, the way that this rule learning system works, and again, I can talk about this sort of offline, is you examine your new environment, you log it, and then you see if there are any new circumstances or new contexts that you can figure out and update your rule base accordingly. And that worked pretty well. We actually tested this on an MIT race car, which is a small self-driving car, and we showed that it could sort of learn new behaviors if it saw different lights or if it saw different behaviors. And so that's the way that the sort of rule part of my system works. But this also relies on using a flexible representation, which is supplemented with Commonsense. And so the representation that I chose to use was something that's a little bit old school. So actually I used primitive representations or a frame-based representation. And what's nice about these is that they have implicit reasonableness rules built in. And I'll talk a little bit about that. So in particular, I used CD or conceptual dependency theory from Schenck. And so the idea with that is that you model the input in terms of in terms of verb primitives that can account for most actions. And again, I was interested in this because we're in the self-driving car space, so we know that there's some movement attached. So what I did was I modeled the 5 primitives for physical actions that include things like ingest, expel, grasp, move, and propel. And then I also extended that to cover different vehicle-specific actions. So things like yielding and turning and different reasonableness rules attached with that. And so for demo purposes of the system, I created a parser that would basically describe what you were perceiving and then put it into the primitive representation that you wanted to use. So again, if we sort of revisit the image that I alluded to in the beginning, so we have this pedestrian crossing the street. This is data from NuScenes. This is a self-driving car data set that I used to validate my thesis work. And maybe you say that this is labeled as a woman, then the description of this image is something like a woman crossing the street. And so I built my own parser basically using a series of regular expressions. And then I bound those to specific anchor points with common sense knowledge. So the idea, again, as I sort of alluded to, is this can represent a lot of different circumstances. So maybe you're not specifically interested that this is a woman crossing the street, but this is a person and they're moving across some street. And so the idea of sort of using this with these abstract terms is, again, so you can represent multiple types of circumstances that are very similar. And so when you put this into a primitive decomposition, what this looks like is basically you've chosen to use the move primitive, you have a general direction, and then a person who's actually doing the moving. And so these primitives have implicit reasonableness rules. So the move primitive basically says that if you're looking at someone moving towards a location, that is reasonable if the actor, so in this case, the person or the woman crossing the street, is adamant and they're located near the location. And again, you can use some common sense for that. You can figure out whether the object has the ability to move, and then the location you can sort of get from the frame that you're looking at. And there are many other sort of primitive reasonableness rules, but I'm just going to focus on movement. And my specific thesis was basically if you could say that a perceived frame is reasonable if all the primitives in that frame were reasonable. And that's sort of important because you're going to have a lot of different objects that are doing a lot of different things in your frame. I'm going to go through an example of what that actually looks like. So how this is actually implemented on the existing data set, so how I actually use this on NuScenes, what you'll largely see is some image like this on the left. So you'll see a bunch of different objects that are doing a bunch of different things. And so these all have their own labels. So the blue boxes are people, the yellow boxes here are vehicles, and then there's some object that is being propelled by this woman. Now, these are all very complex and they all have sort of different theories of mind, but they all have the same sort of general reasonableness rules attached to them. And so when I actually represented that, again, this is in a variant of RDF, basically you can see how this representation caters to this type of data. So the actor, you basically report the actor state. So you say what the vehicle is doing, you report its last state, its current state, and the general direction it's going towards. And then you describe the, basically what the other objects in the scene are doing. So you can describe what the woman and the man here are doing. You can describe that the object is being propelled by the woman to the most left. And then you can also describe the general direction. And then you basically check all of these in a reasonableness monitor, and that's sort of the way that the system works. And again, I didn't really allude to it in here, but the general direction is towards a traffic light. And again, we can sort of get that from the scene itself. Now, the reason that I use this sort of RDF representation is, again, because this fits in nicely with the rules that I'm using. So this RDF caters very nicely to using the rules in AIR, which also caters very nicely to the common sense knowledge base, which also stores information in RDF. So how did I actually test this on existing self-driving data sets? So if you look at the NuScenes data, this is the actual data that comes from the system, and then I'm going to talk about how I use the reasonableness monitor to sort of check this. So you can see it has a lot of information. It tells you the general LiDAR points and different scenes, the size and the rotation. And then you want to basically check whether this output, this human, pedestrian, adult, is reasonable or not. Now, if you just query for the concept, so if you just query for the human, pedestrian, adult, you get a lot of common sense that's very disorganized. In fact, if you just look up a human adult, you'll find that it's capable of helping a child and dressing herself and signing a contract. And this is not exactly the information that you would want to do to support your judgment that this is a human, pedestrian, adult in the self-driving car scene. What you'd actually want is different relations. So you'd want something to say that, you know, an adult is a type of animal, it's a type of person. And so what I also did was I created a filter on this type of common sense knowledge. So you would get the specific knowledge that you would want in the self-driving car domain. So in particular, an adult is a type of animal, and animals have certain qualities attached to them, and their general size. So things like it's bigger than a child. And so you can use that information to justify whether this is reasonable or not. So on this actual data, if you put this into a reasonableness monitor, you will get that this is reasonable. And this is the output explanation. So this is actually what's output from my system. So it says, This perception is reasonable. An adult is typically a large person. They're usually located walking on the street, so it gets that from Commonsense. And then it justifies its dimensions that it gets from the data from NuScenes. The approximate dimension is approximately the correct size in meters. So it knows something about the common sense of general pedestrian sizes. Now, one of the most difficult things in my work, and I'll talk about this a little bit at the end, is that all these data sets are perfectly curated and hand labeled. So one of the problems with that is that there are no errors. So there are no unreasonable labelings in this data set. And so what I did was I basically also created the capability to scramble these labels. And then I wanted to make sure that I could detect and justify that. So if instead this scene is a movable object traffic cone, so I've scrambled that label, then it will come back and say that this is unreasonable. And then this is the reason why. So it finds that the perception is unreasonable, and it sees that the traffic cone located in the center region is not a reasonable size. It is too tall. And there's no common sense that supports this judgment. So there's no way that you were close by. This isn't something like a child versus an adult. This is something that's just clearly wrong. So it actually comes back and says to discount objects detected in that region moving forward. But as I had sort of talked about, this is just one sort of reasonableness monitor on one component of a self-driving car. And there are many other components on a self-driving car that we may want to also explain and justify. And one of those are sensors. So I'm going to talk a little bit about how I did this for sensors and then move towards how I applied this to full system design. So for anyone that works on sensor data of any sort, this is just for self-driving, it's very difficult to understand. This is sort of a bird's eye view of what is perceived in a vehicle of a car. But the actual description of what's going on in this scene is the explanation that we would want to get is something that there's a pedestrian with a pet, a bicycle, a car making a U-turn, lane changes, and a pedestrian crossing in a crosswalk. Now, I don't know about all of you, but there is no way that I was going to figure out that description by just looking at this data. And so basically what I did was I created a sensor data interpreter. So it would be able to look at this sensor data and then develop a qualitative explanation of what it perceived. And I did that using edge detection and some geometric analysis for tracking. And so the idea is that if you perceived something like, a fox crossing the street, instead of just saying that there's an object detected in this region, it would come back and say, oh, it's about 4 feet long, it's about 2 feet tall, and it's moving, and this is the general direction that it's moving. And the idea with that is that you could actually take those qualitative descriptions and then put them into the reasonableness monitor for additional reasoning and justification. So you could actually use these qualitative descriptions in part of the reasonableness monitoring framework. And so there were a lot of issues with applying this to modern day LiDAR, and I'm happy to talk about that offline because it's very dense and very noisy. And so essentially what I did was I actually used a deep neural network as the middle part here. So what I had done in previous simulations, so when we did this in simulation, it worked fairly well, but the LiDAR was fairly sparse. So I was able to do this geometric and qualitative analysis directly. But on this sort of modern day LiDAR, since it's very dense, that doesn't exactly work directly. And so instead, I basically passed that through a deep neural network, which then would give you a bounding box direction and location. So then from that general location and that sort of subset of the image, I'm able to then apply that to the qualitative analysis, and then you get back this sort of qualitative description. So it will tell you the general size and movement, and it'll tell you the general place where it's located. So that's the way that I sort of qualitatively describe these types of sensor data, and you can apply that to LiDAR, you can apply that to radar, and I've actually also applied that to different types of system states, so stopping and braking and things like that. But now sort of the big part of my talk was how did I use these types of qualitative descriptions and justifications and then do that for better system-wide failure detection. And so that's, again, taking reasonableness monitoring and applying it to full system design. And the example that I'm going to be using throughout this part is the Uber self-driving car accident. So again, if you recall what happened, there was a person crossing the street, which unfortunately was struck and killed. And what had actually happened when they looked at the data from the crash was that again, the vision system was oscillating between a bunch of different labels. It was oscillating between a bicycle and an unknown object in a vehicle. And then the LiDAR system had actually detected the person, but they didn't have the sort of qualitative descriptions that I showed. They weren't able to actually interpret what they were perceiving. And so they chose to actually ignore this object. And then unfortunately, the pedestrian was struck and killed. But this is part of a much bigger problem because there is lots of limited internal reasoning in a vehicle. The sort of headline about this was that there were serious safety lapses, which led to this fatal self-driving car crash. Again, that was from the documents from the actual accident itself. But this is just one of many. It was very unfortunate that this was a pedestrian crossing the street because Google has had this issue. So there was a Google self-driving car that had, I think, the first semi-autonomous vehicle crash where they basically didn't expect the bus next to it to move. It classified it as a cloud and thought it wasn't going to move, and so it just ran into it. So it had no idea that, you know, clouds can't be located near it. But then there's the other side. So when you have systems that are too cautious, then you get this sort of herky-jerky behavior. And this is what a lot of vehicle manufacturers have really struggled with, is that they start and stop for everything. So any object that they perceive, whether it's done with LiDAR or vision, they stop suddenly for it without having any sort of common sense. So, you know, you would obviously want to stop for something that's moving across the street, but maybe not a plastic bag or something that you could easily run over. And so my solution has largely been give these components the ability to justify, reason, and explain to themselves, and then put that into a system architecture as sort of a last pass check. So again, I sort of have used this system architecture to reconcile internal disagreements. So I have the organizational architecture, the reasonableness monitors around each part, and then a synthesizer, which is figuring out which parts to trust and not in these sorts of inconsistent situations. So the monitored subsystems combine into the system architecture, and then the synthesizer is able to deal with these sorts of inconsistencies. And the way that the synthesizer deals with inconsistencies is it builds an argument tree, so it figures out what things have to be met for it to be safe for some notion of safety. And then that can be queried for supporting counterfactual. So what's nice, although we haven't tested this completely, is the idea that you could sort of remove and add facts and see what would have happened in different situations. And I think this is really important for debugging these sorts of systems moving forward. And I call this approach anomaly detection through explanations. So the first part is this sort of architectural diagram, but there's also a reasoning component. And that's what's sort of important, especially in self-driving, is how this can be used in sort of real-time analysis. And so the way that this reasoning works is it's largely building, it's usually using the previous parts of the system that I described. So the first thing it does was it is each one of the subsystems and monitored outputs generate symbolic descriptions for each committee or subsystem. Then you take those qualitative descriptions and put them into a local reasonableness monitor for more reasoning and support. And then the synthesizer is able to reconcile inconsistencies between those monitoring outputs. Now, if there are no inconsistencies in those monitoring outputs, the synthesizer will just summarize what has been perceived. And again, that's really important for doing any sort of after-the-fact analysis, especially in autonomous vehicle development. And I'm going to walk through how this is done in the Uber self-driving car accident example, which we simulated, and then I'll talk a little bit about the larger evaluation that we did. So again, I generate these qualitative descriptions for each committee. The vision system automatically outputs these symbolic labels. That's what the vision system does in the car. And again, this was oscillating between things like a vehicle, a bicycle, and an unknown object. Then the LiDAR basically does the geometric analysis, which I just described. So instead of looking at that large point cloud of data, it comes back and it describes that seeing an object moving, it's 5 feet tall, and where it's generally located. So in the top left quadrant in the point of reference of the car. And then I also have applied this sort of qualitative analysis to the vehicle tactics. That's a sort of another project which I didn't get to talk about, but it was in the early part of my PhD, which is basically a way to describe vehicle logs after the fact. So you look at this sort of vehicle log and it will tell you that for the last 10-second history, it's been moving quickly, proceeding straight, and it has continued straight. So I start with those qualitative descriptions, and then I put them into a reasonableness monitor so that they can sort of explain why these are reasonable in their own context, in their old worldview. Keep in mind that the tactics have, you know, a different set of common sense than something like the vision system. And so what this looks like, and I'm showing this in natural language just for demonstration purposes, but this is all stored in symbolic triples. So if you put the vehicle, bike, and the unknown object through a reasonableness monitor, it finds that it's unreasonable. And again, the explanation is that there is no common sense supporting the similarity between a bike, a vehicle, and an unknown object, except that they can be located at the same location. So it finds that, and you know, they're probably located in the same place, but they obviously can't be the same thing. They're not the same size. They don't move in the same way. So this is sort of clearly wrong. So it basically also issues a recommendation to say that this component's output should also be discounted. Now, the LiDAR output, the object moving, the general description of how big it is also put into a reasonableness monitor. It finds that it's reasonable, and it says that the LiDAR perception is reasonable because an object moving of this size is a large moving object and it should be avoided. The LiDAR system doesn't have a whole lot of common sense that's able to support this judgment, but it does say that it's something that should be avoided moving forward. And finally, you can put the qualitative description of the system state. It finds that it's reasonable, and it says that the system state is reasonable given that it's been moving quickly and proceeding straight for the last 10-second history. So it has some common sense. You shouldn't do this sort of starting and stopping behavior. Now, there's obviously an inconsistency here. So that is then put into the explanation synthesizer, which outputs the explanation that I showed at the very beginning. So it finds, so first it recommends something. So it says actually the best option is to veer and slow down because the vehicle is traveling too fast to suddenly stop. The vision system is inconsistent, but the LiDAR system has provided a reasonable and strong claim to avoid that object moving across the street. And again, these are also stored as symbolic reasons. These are just sort of a small subset of that. But you can sort of see where this end explanation comes from, right? You can see it gets some information from the vehicle state, it gets some yellow information from the vision system, and then it obviously gets a little bit of information from the LiDAR system as well. But how does the synthesizer decide what is important, right? This seems like sort of a magical black box. It has to have some existing knowledge. So as I sort of described, the synthesizer is meant to deal with these sorts of inconsistencies, or it summarizes what it's perceived, and it does that by building an argument tree. And then that can also be queried for support and counterfactuals. But to be able to build that argument tree, it basically has to be given some sort of priority hierarchy, which then can be turned into abstract rules that must be met for different transition states. And so the priority hierarchy that I used was basically a 4-part hierarchy that prioritizes passenger safety, and then passenger perceived safety, and comfort, and then efficiency. And so that I'm going to focus on passenger safety just for this talk. I could talk about how all the other sort of priorities are used here. And that is turned into the abstract goal that a passenger is safe if the vehicle is going smoothly, so it's proceeding in the same speed and direction, right? That's sort of avoiding the herky-jerky behavior, as well as the vehicle avoids threatening objects. Now, keep in mind this priority hierarchy is intentionally vague. It's meant to be vague so we don't deal with the sort of ethical issues that a lot of people have been worrying about for autonomous vehicles. But if that's something that's of interest, you can just define your priority hierarchy as detailed as you want, as long as you have the sort of rules attached with it. So I'm going to talk about how this is actually done. So again, what we want to get out of here is that a passenger is safe if it's a smooth ride and it avoids threatening objects. And so I largely represent that in first order logic. So basically, if between 2 successive states, S and T, you want to be moving at the same qualitative speed here. And then you want to make sure that there are no objects that are a threat in either state. Then you can sort of say that the passenger has the property that it is safe. Now, again, we have to define what does it mean for some object to be a threat. And again, I define that in first order logic. So I said that an object is a threat if it is moving, if it's located near where you are, so it has to be within some proximity, and that can be changed given what domain you're in. And then it has to be some sort of large object. And that's how I defined it to be a threat. Now, again, this is in the self-driving car literature, but this could be defined for many different domains or applications given what you perceive as a threat. And so then using this, I'm basically able to represent this as a very abstract goal tree. So the abstract goal tree basically says that a passenger is safe if it has safe transitions and no threatening objects. The safe transitions, the backbone of this is this first order logic. And then avoiding threatening objects is basically that definition of a threat that I showed earlier. And so just the way that this looks in terms of a goal tree is basically I listed this in a set of rules. I wrote my own rule language so that I could basically bind these to the specific conditions I was looking at. And then I backwards chain that. So I basically say that I need to meet the, it needs to be that the passenger is safe. And then I create an and or tree. So basically I say that a passenger is safe at some speed v between two states, as long as this and or tree is sort of satisfied. And there are many different ways to do this, and this can become arbitrarily complicated for different situations. So again, for purpose of presentation, I'm going to sort of focus on this abstract goal tree. And the actual reasoning that happens here is that the not threatening objects has been triggered by the LiDAR subsystem. So because the LiDAR system interpreted what it was perceiving as sort of a large moving object, it finds that this is not met. And so what's important here is that it's not necessarily saying that the vision system is wrong, but it's saying that the LiDAR system is a stronger argument. And that's what's really important, because you largely have this sort of unreliable behavior between parts. And so it basically finds which one is more believable, especially in these safety critical situations. And that's eventually what leads to this final explanation. Now, I evaluated this largely in simulation. For good reason, I wasn't able to put this on a self-driving car. We just can't put them into these sorts of erroneous situations. And the types of errors that I was interested in just can't really be mimicked on the small autonomous MIT race car that we had previously looked at for doing this type of analysis. And so with my undergraduate student, Vishnu, we actually put this onto Carla. This is a vehicle simulator. And you'll see sort of in the distance, there is a red object that's moving. That's a person crossing the street. The vehicle sort of starts to swerve and then eventually goes through the way, or veers out of the way. And you can see here at the very bottom, it actually finds that anomaly detected with plenty of time to be able to swerve out of the way. Now, for people who are interested in the details of this, no, it is not a human crossing the street with a bicycle, but Carla, the vehicle simulator, didn't have the capability to have a person holding a bicycle crossing the street. So I made sure that it actually was able to reason about this situation after the fact. So I added a little bit of distance in the detection to make sure that it actually mimicked that example. And so this is one part of the evaluation of my system, were these sorts of real world inspired scenarios. I've also looked at a lot of different pre-crash scenarios. So NHTSA put out this guide of different difficult vehicle situations that you should be able to reason about. And we've simulated some of them and been able to explain them after the fact. But I also wanted to make sure that it could sort of reconcile these types of inconsistencies, especially in larger data sets. So one of this was this sort of detection, which was generating these logs from scenarios and then detecting failures, which is what I did with these NHTSA pre-crash scenarios and the Uber self-driving car accident. But I also inserted errors. So I talked about how I basically took the NuScenes data set and then scrambled the different labels to give them different errors to make sure I could detect them. And then I'm also interested in looking at real errors. So what I wanted to do was examine errors on some of these self-driving car challenges. So I wanted to look at the existing algorithms and see where they failed. But unfortunately, many of these are not open source. And the other thing is many of them are looking at multiple pieces of information that I may not have access to. And so that was sort of one of the issues with that. And this has been a big problem. You know, there aren't very good error detection and anomaly detection data sets, especially for self-driving, because they're all hand curated. So actually detecting errors in simulation is sort of the most reasonable thing to do moving forward. And now to sort of summarize and conclude my talk, I just wanted to talk a little bit about my, my vision, which is basically to create systems that are articulate by design. And I started this talk by talking about the problem that complex systems are imperfect and they fail in complex ways. And what I've talked about as a solution is an explanation. Now, if you look at the space of the explanatory AI literature, and I led a review paper on this, what you'll see is that everyone is really explaining something different, and they're all doing this after the fact explanation analysis and justifying why these decisions are right. They're largely not looking at explaining errors. And in fact, if you look at what I've developed, I've created explanations that are dynamic. I talked about how these can be queried for counterfactuals, and this is under uncertainty. So a lot of these are unknown, and a lot of the situations I've looked at, they have immense amounts of noise and uncertainty. And then also I created an architecture that uses explanations. So these are not just after the fact explanations, but actually explanations that can be used to aid decision making. And that's what I argue is necessary to make machines that can actually communicate. And this isn't just communication between a human and a computer, but also with other systems. There's been a lot of work on sort of figuring out where opaque learning systems and machine learning sort of thrive and where symbolic systems are better. And what I looked at was largely taking the output of a learning system and putting that into a symbolic system to do a last pass check to figure out whether it's behaving reasonably or not. But what I actually would want is to use explanations between them as a common language to complete tasks. This is important for redundancy. These systems solve problems in different ways, and it would be really nice if they could sort of learn from each other. And also to actually have hybrid processes, so systems that could actually learn different ways to solve problems from each other. But the other area is sort of thinking about communication with humans. And I argue that explanations are largely a debugging language. So this is debugging so that humans can improve complex systems so that they can sort of figure out where they're doing things wrong and right. But also for education. It's been shown that a lot of these opaque processes are very good at finding trends that we could never find. This has been shown in cancer detection and image recognition. And it would be really great if these systems could actually say why they think that these images are cancerous or not. And maybe humans could be educated in new ways to sort of solve these problems. And the impact is basically for the confidence and integrity of systems. And this is important for society so that systems can communicate with humans and share tasks, especially important for self-driving, where you're going to have this sort of handoff problem between an autonomous agent and a human driver, as well as for liability. The project that I worked on during my PhD, The Car Can Explain, was actually all about liability. It was to create these systems that could actually testify and answer questions and provide insights, especially in the case of an accident. But I argue this is also important for robustness. I actually think that these sorts of architectures are really important to harden the security of systems so that you can do dynamic detection of failure and intrusion with precise mitigation. So instead of flagging everything as sort of an anomalous situation, can use explanations to do intrusion and mitigation more precisely. And so the contributions of what I've been working on, I started by describing this problem that complex systems are imperfect. And I did that by describing the need for local sanity checks as well as communication amongst parts to reconcile these types of inconsistent behaviors internally. I then talked about a way to figure out when opaque systems are behaving badly using local subsystem monitors. And then I described how I put that into a full system architecture. So how I created a full system architecture of self-explaining agents along with a high-level explanation synthesizer that can reconcile these inconsistencies amongst parts. And so what I did was basically create this sort of a system-wide monitoring architecture that used explanations as this sort of internal language. And finally, through simulation, I showed how this can do more robust failure reporting. And so I really am happy to be here and talk about this sort of new view of error and anomaly detection. And in the remaining few minutes, I would be happy to entertain questions.
Thank you very much. Do anybody have questions? Go ahead and unmute yourselves.
Hi, thanks for a nice talk. I wondered, is there any way that you can get some kind of quantitative analysis of the work that you did?
Yeah, that's a great question. So that's something we've been working on. It's been very difficult just because some of these, so I guess looking at the self-driving car domain, there have just been so few autonomous vehicle accidents, only 3 or so that have been reported. So all we can sort of do is simulate that and explain it after the fact.
You could have
So
something more intrinsic, though, perhaps.
yeah, so one thing we did was we basically created the sort of like scrambling system that would basically invoke errors in some of these existing data sets and then look at how well I could detect and explain them. And we've also looked at a user study to sort of figure out how useful those explanations are, although that's just sort of a local approach. My undergraduate student Vishnu and I are now thinking about a way that you can actually score reasonability. And that's a little bit different because it's always changing in context. So it's very, how do I say it? It's sort of difficult to give it a measure naively, and people have different sort of thresholds for that. But yeah, so largely the sort of error scrambling is the large quantitative measure that we've done so far.
I have a question. So Leilani, really nice talk. It was really interesting. One question I have is, okay, will this scale? So, I mean, if you were going to put this on a self-driving car today, right, are you going to be able to run this fast enough that you could actually reason about all the situations that arise?
Yeah, so that's also a great question. And again, we've only been able to simulate, a few things in simulation, and it worked pretty well. I showed the real-time simulation and it detected it with just enough time. One of the issues that we had when we applied this on the MIT race car, like a very small autonomous driving agent, is the rule set did explode. So it would keep learning new rules and new behaviors as it kept driving. And that rule set got very, very large very quickly, which is sort of expected. And so we've sort of thought about ways to prune the rule set. That's what we saw as sort of the major deterrent to actually applying it on like a real existing architecture. And we got fairly far on that, but not enough to sort of publish it. But basically, to answer your question is, in simulation, it did fairly well, but we haven't been able to sort of test it across the board yet.
Okay, thanks.
I have a question too.
Go ahead, Pedro.
Okay, so this is interesting. So one of the things that I worry about is that the knowledge-based systems are so notoriously brittle, and so that has been a problem for 30 years. That the knowledge base is incomplete, that the rules are incomplete, that maybe the rules are wrong. Mm-hmm. And you have something that learns rules, it could learn wrong rules. And the knowledge base, ConceptNet also has errors. And so I wonder, I mean, have you studied what are the effects of these problems? Because, I mean, neural systems will make one class of errors, but your rule-based system will also make errors. And how do we know that the errors that the knowledge-based system makes are less severe than the errors that the neural system makes?
Yeah, it's a great point. And I've had a lot of issues with ConceptNet. As you said, a lot of the data points that it has are just wrong. I was looking at doing some temporal analysis the other day, and it said that the days of the week were in the wrong order. It was just wild. So you can't sort of always trust anything in this sort of case, especially with these rule-based sort of knowledge-based systems. But what I will say is that the purpose of my system is not to be a sort of standalone system, right? It was meant to be a sort of last pass check with as few rules as possible to just make sure that these systems avoid these safety critical, mission critical failures. And with that, it has worked fairly well. I will say, it did take a fair amount of hacking. As I said, like a lot of it is pruning common sense, making sure that the rules are correct. And I think if this is to be deployed, there is going to be a fair amount of human intervention. As you said, there's going to need to be a human who's constantly verifying, yes, these rules are correct. Yes, this is something you want to make. And I think that's part of the issue with deploying these types of systems. But as for the specific circumstances I was looking at, because I assume that the underlying systems work fairly well, I mean, these image recognition systems on vehicles work fairly well. over 90% of the time, it did fairly well with just finding that, 8 to 10% where it failed, so.
Question. You mentioned that there are only, a very few numbers of actual accidents. Have you thought about expanding it in some sense to something that's a non-accident, to kind of mimic the way a driver actually learns? I mean, when we come close to an accident, we learn something.
Yes. So you're asking about how the system would work on someone who's perceiving something. So maybe not necessarily a part of the system. Is that correct?
Not necessarily. I'm just saying that a human, if I don't have an automated system, I learn. I almost had an accident, so I'll change my behavior.
Yeah.
And can you expand? And I know that's really hard, but expand and essentially help your system learn faster instead of looking at something that is an actual accident. Expand and look at a much wider variety of things. Well, I really came close to an accident. Should I have done something earlier?
Yeah, that's a great point. I guess, we did a little bit of that in the rule learning system. So that was sort of the idea, is that, could you learn from what you were perceiving? If you sort of explained everything that you perceived, would you be able to learn new behaviors? And the idea wasn't necessarily to perceive accidents or other scenarios that you may be able to avoid, but just to learn new behaviors. But yeah, I think you're right. It would be interesting to sort of use that as sort of a meta learning process to improve behavior as well. We just haven't explored that, so.
So I have a question regarding sort of complex systems. You pose this, the idea is to really reason about when the system is extremely complex.
Mm-hmm.
The example which, with the cycle crossing the street, it seemed like the answer was, there was a right answer. Like if you veered on the side, you could actually avoid the object.
Mm-hmm.
Sometimes there is no right answer. If there was a car on your left, then you really have to reason between, do I dash into the car and have an accident there, or do I continue with this object which I can't clearly recognize?
Mm-hmm.
Have you thought about, when the system gets, when you don't have a right answer, where there is no way to avoid it?
Yeah, that's also a great question. Again, it's been very difficult to sort of do this in simulation, but one thing I've been thinking about as an evaluation is to think about how the synthesizer could deal with negotiation. So in negotiation, there may not be a right answer, but there may be ones that are better than others given different constraints. And that's sort of what I've actually been evaluating now. So, if you can create this abstract goal tree for a negotiation between someone, for a job, or someone, to buy a house or sell a used car, maybe there's, maybe they never reach an agreement, but can you show with, adding or taking away different information, you get to a better solution or not? And in terms of the self-driving car literature, we have looked at that a little bit. I'm working with some people on a concept they call anticipatory thinking for cognitive systems. And we're actually working on phrasing these types of challenges for autonomous vehicles. And that's one of them, is what happens when, you have someone crossing the street and you have a car next to you, and you can't necessarily swerve, but you need to slow down. What do you sort of value? So I've been thinking about those problems. I haven't necessarily thought of the solution in the self-driving car space, but I have thought about that in the sort of negotiation, argumentation space.
So one question about the Uber example.
Mm-hmm.
So my understanding from what I've read is that they actually gave priority to the LiDAR system and would have stopped, but they turned that feature off or disabled it because of the number of frequent extraneous stops.
Mm-hmm.
So you've added common sense rules that now would have addressed that particular scenario.
Mm-hmm.
But I guess I didn't quite understand from your methodology. Do you have any way to judge how many false positives, if your common sense rules were in place, would have been incurred, and would the drivers have gotten pissed off at your system too?
Yeah, so that's a great question. I haven't been able to do a super large scale analysis of this system as of yet, so I can't really say,
Okay.
in terms of a larger space. But the question you bring up is a very good one. And because I have these, so because the priorities I look at are so high level, and because they're looking at specific safety, they do have to meet those safety constraints. So, you know, it's not going to start and stop for everything in the road. It's only going to be for my definition of a threat. It's going to intervene. So for that, you know, we haven't had that many false positives, although in the quantitative analysis, I should say, because I was just adding a little bit of noise, and I'm happy to talk about this more offline. When I scrambled the labels, I was doing very close by detections, because I didn't want to replace a traffic cone with something like a 2-ton truck. That's just very clear to detect. And because I was just adding a little bit of noise, both to the LiDAR and the vision, we do get a fair amount of false positives. It's not much. It's about 4% on, it was about 10,000 samples. And you can imagine that would be fairly infuriating, but I sort of reasoned that away because I was just adding a little bit of noise, so it's going to be wrong some of the time.
Okay, thank you.
Aram, I think you had a question.
Yeah, I have a quick question actually. So how transferable is this to a different domain? So let's say if instead of self-driving cars, you wanted to basically apply this type of reasoning to I don't know, some cybersecurity monitoring systems that does some mistakes, and you like to understand what are the reasons. So how easy would it be to kind of transfer this approach to the domain?
Yeah, so I'm actually writing that up now, so I'm glad you asked that. So I've been sort of thinking about what you would need to change in terms of these different applications. And as I sort of alluded to, I've been trying to apply this to human negotiation and argumentation as well. And so largely, you know, the architecture is fairly transferable, but the rules aren't necessarily, right? If you're looking at you know, cybersecurity or different types of logs of that nature, your event analysis is completely different, as well as your sort of common sense rules, right? You're not necessarily looking for objects like you are in self-driving cars, so you would need to sort of figure out what those rules are. Now, the rule learning would work just the same, but you do need to start with that baseline of rules. So I guess the biggest thing is that you'd have to define your architecture. So you'd have to sort of describe, you know, what the hierarchy is in the system you're looking at. And then you'd have to describe the baseline rules and the basic ontology. So what sort of events are you looking for?
All right, thank you.
Hi, so have you considered putting this type of intelligence into the infrastructure instead of the cars? So one can imagine like a yield situation. If you had intelligent reasoning inside of the yield signs themselves, right? Yield signs were made for human consumers, whereas in a machine-driven world, you would want signals that are defined or focused on machines. And so have you looked at that aspect of trying to make the infrastructure intelligent? Because a yield system, if the intelligence were built there, it could do much better than a car that is trying to kind of identify all situations at all times.
Yeah, that's a great point. So you're sort of asking what would happen if we're like receiving signals from some of the different objects that the vehicle is perceiving, is that?
Yeah, or just to put this mechanism, like the same rules still apply, right? You want to be able to detect objects that aren't normally in the yield zone and things like that. But if it was tuned to a local environment that only needs to really understand that local environment, it would probably do much better than a moving car that has to deal with everything.
Yeah,
I could send a signal to that car.
So that's a great point. So I haven't, you know, to be honest, I haven't looked at that. I've sort of thought about that, especially in terms of a test bed, especially when we were sort of testing this on a robotic system, creating our own sort of driving world, if you will. But I think that's a great point. I hadn't really looked at the external signals or what that would even look like for the system. But my intelligent guess would be, I think it would work fairly well. But again, I think there are always going to be false positives. You can't assume that every signal is perfect. But yeah, that's a very good idea. I will definitely consider that.
Thanks.
So first of all, great talk. It was really interesting. Could you discuss a little bit about, you mentioned, or Aram asked a question about applicability to other domains. Do you have any thoughts or feelings about how quickly your system might ingest rules that are already defined in other domains in either a structured or semi-structured way? Like if that can be adapted quickly for the reasoner, et cetera?
Yeah, I'm actually another great question because that's what I'm working on. So I'm trying to see how it can take in different rules in different languages as well. Part of this system was in a rule language I built. Part of this is in air. There are issues with trying to get those to work together. So the short answer is I don't know. But I think, you know, for individual rules, I have basically ways to, if you were just adding a rule or taking one away, it's fairly quick. But I do think if you're adding a whole new set of rules, it shouldn't be too difficult because it's not doing much inference at the very beginning. So it should be able to ingest them fairly quickly, but I'm not sure about how to sort of, how that would work in a working system. Like I think if you start with a new set, it should catch up fairly quickly, but I'm not sure in a system that's already been working.
Thank you.
Mm-hmm.
All right, well, I think we should wrap up because we have a full day and a half for Leilani to meet with a number of us. So thank you very much for attending, and we look forward to following up more later.
Great, thanks.